Okay, these are the general coverage about resistance components. We also discussed about viscosity, viscous effects, boundary layer formation, type of shapes based on which the resistance estimation should be performed. Now coming to the details of the components of resistance, first we look into the frictional resistance. Viscosity of fluid causes friction. We know that, we have already discussed. Viscosity results in sharing of layers between the layers, and between the fluid layer adjacent to the body and the body there will be a shearing effect. This shearing effect leads to a tangential stress. You know that tau is equal to mu into dou u by dou y. That is a relation for Newtonian fluid. So that tau is a shear stress. If you integrate the shear stress over the wetted surface of the ship, you get a resultant frictional force which opposes the motion of the vessel, that is due to the viscosity. So this again depends on the type of fluid. If what now here we consider water. So here the only option when you consider for ships is whether it is in fresh water or sea water, that difference matters, but you do not envisage any other fluid in which ship operates, isn't it, except air and water. The flow pattern, what type of flow, that is it turbulent, is it laminar, what is the flow pattern, depending on which viscous effect changes, frictional resistance changes. Frictional resistance is obtained by integration of the tangential stress, that is what I said before. So it is by integrating the tangential stresses over the wetted surface of that. So for ideal fluid there is no friction because there is no viscosity, so that is obvious. That is what we discussed in relation to D'Alembert paradox. Now we just explain this viscous effect here. We consider two plates, one is stationary, you can see that bottom is a stationary plate and the top one is a moving plate with a constant speed of v. So here we consider there is no pressure variations or pressure gradient over this between the two plates. If there is a pressure gradient there will be a velocity. Now only thing, the flow is induced not by pressure gradient, it is induced by the plate moving. It is a still water, you have one plate which is stationary, you have another plate which is moving with a constant speed. So here that means the flow adjacent, the fluid particle adjacent to the plate attains the velocity of the plate, isn't it. So if the plate is stationary, the fluid particle adjacent to that gets a 0 velocity. If the plate is moving with the velocity v, the fluid particle adjacent to that plate will get the same velocity as the plate. So you have v here and here you have 0, and in between it varies in the linear form like this. So this is the flow variation across these two plates when the one plate is stationary and other plate is moving. So that is what this is, no slip condition between the fluid and plate. That means, what does it mean? That is what I said, the fluid particle does not slip, there is no slip with the boundary, that means it attains the same velocity as the body. So that is what you call the no slip condition. The layers of fluid in contact with the plates have no relative velocity, that means it will have the same velocity as a plate. So that is why you have the 0 velocity here and the plate velocity here for the fluid particle. The fluid is displaced in such a way that the various layers in the fluid uniformly slide over one another. So that is why you said uniformly you have a linear variation. So each layer will slide with a uniform variation gradient. So if you look to that velocity, it is a velocity at the layer at a distance y from the plate, that is if you look here, this is the u small u, that is a velocity at any position, then this is a y done, then this is a distance separation of the plate, that is h, that separation. So the velocity at any distance you can give u is equal to y by h into v, because it is the linear variation. So this is the velocity, and the force F is equal to, this is the dynamic viscosity into S into V by H. S is the surface area of the plate here, and H, you have seen that V by H, this relation gives the velocity gradient here. You can see it is coming from this is a relation which I mentioned, shear stress tau is equal to mu into dou u by dou y, you know this relation. So this is a relation which defines the Newtonian fluid, okay. And if you know the stress, this is the stress, stress into area gives the stress is equal to stress into area gives the force. So you get this relation from this one using the relation over here. So you just get this relation, the force that has to act on the moving plate to maintain the motion is given by this, which is coming from this relation and substituting this over that. This force is equal to the resistance offered to the displacement of the plate, okay, that is for the movement of the plate. So and that it is, we are not considering any wave making or anything here, this is due to the tangential stress or shearing force opposing the plate motion. It has to overcome that and move the plate. So this is the force required to move the plate. So when you look to the boundary layer, the region of the fluid close to the ship wetter surface, boundary layer, you know that it is very close to the ship surface, depending on the type of surface, depending on the speed and all that, boundary layer thickness varies, but usually the thickness is quite small compared to the ship dimensions. So in this boundary layer the shearing effect is significant. We have already seen the velocity gradient in the over the surface, the velocity gradient is strong, and you know that boundary layer definition itself is that flow velocity transition from 0 at the body to the free stream velocity, that is usually taken as 99% of the free stream velocity, that is the point of boundary layer. So in that region there is a velocity gradient, and when there is a velocity gradient, there will be a shear stress, that is this quantity is there inside the boundary layer. So that means there will be a shear stress inside that boundary layer. So the boundary layer may be laminar, as said, it can be, you know, the laminar and turbulent or maybe transitional also. So it can, depending on the Reynolds number, body surface, body pattern, or body curvature, and flow velocity and all that, body size, everything matters here. So this depends on the flow velocity u, body size L, and surface roughness. So all this matters for the type of boundary condition, whether it is laminar or turbulent or a transition. The velocity of the fluid just at the surface of the plate will be due to frictional forces. So at the body surface it is due to the friction forces, there is a shearing of the layers which leads to shear stress and lead to frictional force. So you have already seen that the fluid velocity distribution, it is 0 at the body, then it increases, and then finally it reaches a free stream condition. So that is how the flow gets, you know, the inside boundary layer flow varies. This is a picture for that. You can see that this is a, if you take a, this is a boundary layer, and you see this is a velocity profile, this is a wall which is stationary. So this 0 velocity here at the wall, but away from the wall it has to attain the free stream velocity. So this is a free stream velocity. So here it should be free stream. So the transition from here 0 to the free stream velocity here, and this point this taken as 99% of the free stream velocity. So when it comes here, the line is missing here, So here this point is a 99% of the free stream velocity, and here this is a 99% of. So you connect all these 99% u infinity points, you get the boundary layer. There is no physical boundary there, it is only a assumption, so that it is easy to calculate or manipulate the viscous effect. So because one of the advantages, if it is a real fluid, if it is an ideal fluid, viscosity complexity can be avoided in the mathematical formulation. So you need to consider the real fluid cases inside the boundary layer, and outside the boundary layer often people deal it as potential flow, where the formulation is rather easy and computation become less tedious. So that is the reason. So this I have already explained, and we have seen that it is taken the velocity profile of the boundary layer appears to be like this. The wall is treated as stationary here, and 0 velocity here at the adjacent to the wall for the fluid particle, and this is the point where you have the velocity getting to 99%. So similarly you get the profile over the along the length of the wall or over the body, and then you join the points at 99% of free stream velocity and connect these points with the line which you say it is a boundary layer. So inside the boundary layer the viscous effect is more, and outside the boundary layer you have the viscous effect not significant, and often the flow analysis is performed using potential flow theory away from the boundary layer, and inside the boundary layer can be treated as a real fluid, and where Navier-Stokes equation should be applied. Loss of momentum flow, you can just look into the forces coming on this surface due to the viscous effect. You were considering a volume element just aft of the plate, that is what is the change of momentum occurring to the fluid when it crosses over the plate, before the plate and after the plate. So the change in momentum of the body is obviously the frictional force coming on the plate. So here this is represented by the momentum equation here, that is look to what is the loss of momentum occurring to the fluid volume when it passes over the plate. So that is equal to the resistance of the plate. So here you can see that this represents the momentum change of the fluid component. This is integrated over the boundary layer thickness, delta is a boundary layer thickness. So this will is equal to the total shear stress integrated over the length of the plate, which gives the total force, resistance force, that is due to the frictional force. So here it gets written as a Rf is the frictional resistance along the plate, and tau it is coming from the relation of a relation for Newtonian fluid, which is the shear stress is proportional to velocity gradient, and it is taken at 0, which obviously refers to that at the wall. So frictional resistance usually most okay, this is if you know the coefficient of frictional resistance, or Cf is a specific frictional resistance coefficient, and frictional resistance, or called as frictional resistance coefficient, and Cfs is equal to frictional resistance Rf divided by half rho Sv square, where S is the wetter surface, rho is the density of fluid, and V is the flow velocity. And here this Cf depends on nature of flow, that is whether it is laminar flow or turbulent flow or transition region, that depends on that, which again in turn depends on Reynolds number. Then form of the surface, that is what is the shape, how streamlined the shape is, where there is an abrupt change in the continuity and all that also matters, and because whenever there is a sudden change in the curvature there will be a flow separation, then the flow separation results to subsequent increase in resistance. Then character and condition of a surface, that is whether it is a smooth surface or rough surface, depending on which the frictional coefficient differs. So all these parameters contribute to the resultant frictional resistance. So if you look to the boundary layer, now the intention is to find out what is the relation of this frictional resistance with reference to velocity. Here that is the boundary layer velocity distribution. You can see that here is a y by delta, that is distance inside the boundary layer divided by the boundary layer thickness, and here you have the velocity, proportional velocity, that is u by small u by capital U is the free stream velocity. So that means that away from the boundary layer it reaches 1, that is the free stream, the boundary layer velocity goes to free stream velocity. So this is the distribution in laminar flow condition, and this one is in the turbulent condition. You can see that in both cases is coming to 0 at the surface, that is when this value is equal to 0. Then the velocity distribution of the planes depends on the fluid viscosity. Of course, is a variation, velocity profile will be different for different fluid. So it will depends on the viscosity, again depending on density, then and also the frictional forces again depending on the surface type. We have seen that other parameters. The frictional resistance vary with the velocity raised to power n, that is v power n is the value of n we have to find out, and Prandtl and Schlisting, they are based on their experimental studies, they have came up with a factor of n 1.75 for the value of n, that is the frictional resistance based on their studies proportional to v power 1.75. So that is the conclusion based on their experimental studies, but it got revised later, we see that subsequently. So the velocity distribution, if the velocity distribution here is expressed by this, u is equal to at any point within the boundary layer is equal to u max, that is a free stream velocity, then y by delta power n, and this value of n is, that is what they have put forward as 1.75. Yes, I think okay. The boundary layer thickness for the flow, that is a von Karman expression for boundary layer thickness is given by this expression over here, delta, the boundary layer thickness given by this, and the parameters we have already explained, where L is the length of the plate and all that. So here value of n taken for different plate surfaces, you can see that how the value of n varies for different surfaces. If it is for varnished and polished steel surface, it is power 1 by 9, and for clean surface for merchant ships 1 by 7, for smooth polished surface of wax, plastic or wood models which are used for experiments. So there it is 2 by 11, and here surface covered with long grass, that is basically accumulation of barnacles or seaweeds. So it may resemble to that stage. So it is more rough due to the operation nature. So the power of n is equal to 1 by 5. So this is all based on their studies. They have done towed plate of different sizes at different speeds with the different surfaces, and they have consolidated the experimental results and came up with this relation. You can see what is the flow separation. We have already discussed about what is flow separation. The flow separation, you see the boundary layer, the dotted line here is a boundary layer, and here you can see this is a plate over which there is a flow occurring. This is a free stream velocity is given by u, so it is moving like that. So here you can see the velocity profile. So here this is 99%, here it moves, the boundary layer build up over along the length, and boundary layer thickness increases towards the rear end of the plate, or the flow, or in the case of ship it is the aft, towards aft the boundary layer thickness increases. So the velocity gradient here gives an indication for the point of flow separation. So here you can see it is a positive gradient, the velocity gradient. When it comes here, the velocity gradient is almost it is a 0, it is joining tangentially at the bottom where it is a 0, that is actually the point of initiation of flow separation. And when it goes further down, you get, it is a negative velocity gradient which gives a clear indication that the flow already separated. So that is the what, then the flow gets a vortex, eddies are formed in the flow once the flow separates. So here the flow solids are detect adverse longitudinal pressure velocity gradient, that is you see that there is an adverse flow or velocity gradient. It can occur maybe due to the sudden change in the form of the body. If the curvature about the flow is going across the body, all of a sudden the curvature of the body changes, then flow separates. There also that is there is a sudden change in the velocity, or also there is a sudden change in the pressure. So when an adverse longitudinal pressure velocity gradient results in flow separation. A sudden change of the direction of curvature of the surface, that is what I just explained. So sudden change in the curvature also results in the flow separation. So once the flow separates, eddies are formed and you get a reverse flow, that is what you are saying, the flow is getting a reverse flow here. So that is how the eddies are formed. The flow separation in boundary layer remains thin until the flow separates. You have seen that from the that here it usually small, and as when the flow separates, the boundary layer thickness jumps up, it increases drastically. The velocity profile slope at the wall will decrease when the flow comes nearer to the point of separation. That also we have seen, when the velocity gradient here it is more, here it is reducing, and here it has become 0. So at the point it keep reducing towards the point, and then it changes to a negative velocity gradient. So that is what is said, it's at this point it has become negative when when the flow separates. Then near the wall in the downstream area the reversal of flow occurs, that is you can see that the downstream here this side the reversal of flow occurs in the boundary layer. Also the boundary layer thickness increases rather quickly, that also we have seen from the diagram. What is the effect of Reynolds number on flow? Generally there is a non-dimensional number which is being used for, that is VL by nu. V is the velocity of the flow, L is the characteristic length of the body, and nu is the kinematic viscosity of the fluid, which is equal to mu by rho. Mu is the dynamic viscosity and rho is the density. So that is the definition of a kinematic viscosity. So here at a very low Reynolds number, the flow is orderly and layer wise. So it is a laminar flow in the when the Reynolds number is low. As it increases, the flow tends to separate. We have seen that we can see that when the flow is that is even in the previous diagram, you can see that this is a region, if you look to the local length, this is a region with the up to this, if you consider the length is small. So Reynolds number is small, flow is laminar. When you consider length at this point, the length is large, Reynolds number is higher. So we can interpret the flow pattern also with a reference to the place where it occurs and what is the length at that point. Then as the Reynolds number increases, the flow tends to separate. So which becomes, that is the flow become, boundary layer become turbulent and flow separates. Separation takes place at a periodic way by way of shedding common vortices. So you say that vortex are shed when the flow separates. Then if you increase the Reynolds number further very high, then naturally it becomes the completely fully separated flow you get. Right. So the what is formed, that is the effect of Reynolds number on, that is when the Reynolds number is low, the flow is laminar. When the Reynolds number increases, the flow become turbulent and the boundary layer separates. And usually for ships, if the Reynolds number is less than 10 power 5, we treat it as a laminar region, and if it is more than 10 power 6, it is generally it is a turbulent region, and between 10 power 5 and 6 it is a transition period. So transition region for the flow. So experimental determination of this frictional resistance, just see that the experiments carried out by William Fruit, you can see that it is nearly 1.5 century old experiments. So the what he did is he towed plates of different sizes and different width at different speeds in a towing tank and measured the force coming or tow force required for that. So, when the plate is there and it is sufficiently submerged, the velocity, the wave making effect is negligible. So, only thing coming is frictional resistance. There is no form, plate is 2D, so there is no form resistance coming there. So, only the frictional resistance coming there. So, you can, when it is towed, you can measure the force coming on the tow rope, and that tow rope pull is equal to the resistance offered by the plate at different speeds. So, collect the data for that and then consolidate the data and analyze the data, and he put forward a formula for the experiment for the determination of frictional resistance. So, that is what he said. He used boards of various lengths 15 meters coated with various substances. We have seen that depending on the surface there will be a change in the resistance. Towed at different speeds through fresh water, I have already explained. So, you know R of the total frictional resistance is proportional to surface area and also velocity power run. F is taken as a constant. So, later his son he came up with a, I think this is 1888, it is not 1988. So, he came up with determined the value of n as 1.825. So, he put the value of n as 1.825. So, this is still like an accepted value for n, which is still used. So, various groups performed experiments using plates and mainly 2D plates and all that. So, they came up with different expressions for the estimation of a frictional resistance coefficient, and this is the one we put forward by Schoner, and this is the Cf is a frictional coefficient, Reynolds number is a factor here. So, this is the expression given for the frictional resistance. Hughes formula, he came up with the formula Cf is equal to 0.067 divided by log r n minus to the whole power 2. So, this is the expression put forward by Hughes. So, ITTC, you know, it is the International Towing Tank Conference, that is the organization of people owning towing tanks, and they formed a group international for standardization basically for the towing tank operation. So, most of the towing tanks, they have to, if they are interested in getting a standardization approval, international approval for the facility, they become a member of ITTC. To become a member of ITTC, they have to undergo different calibration tests and everything for the tank, and after that, if it is within the acceptable standards of ITTC, they allow the organization to form a as a member in ITTC. So, ITTC what it did is it appoint a committee to study the frictional resistance, wanted to adopt a formula or come out with a formula, handy formula to find out the frictional resistance. So, a committee, the responsibility of the committee was to look into the experimental activities and also the relations brought out from their activities to estimate the frictional resistance, and then suggest which formula should be adopted by ITTC to estimate frictional resistance coefficient. So, this committee went through various formulae and research groups, and including Hughes formula and all that, and finally, they came up with the relation that Cf better be represented using this formula, that is Cf is equal to 0.075, whereas Hughes used 0.067. After their study, they have put forward this is the formula which is appropriate. That time in 1957, they said it is a tentative or it is a temporary suggestion. Subsequently, based on further advancement in the research and experience, this can be revised, but thing is the fact is still the formula remains same, still it is being used even now. So, that is a expression for given put forward by IDDC, that is CF value can be estimated. Why the CF value need to be estimated from experiment? Because CF is a frictional resistance coefficient, friction depends on the viscous property of the fluid. If you want to consider viscous property of the fluid, you have to consider the real fluid particle motion. Real fluid particle motion is dealt only with Navier-Stokes equation. Solution of Navier-Stokes equation numerically even now to its entirety is not possible. So, you just imagine that getting a numerical solution for frictional resistance coefficient estimation is ruled out, and hence people depend on experiment. So, that is why experiments have been done and frictional resistance coefficient expressions have been brought out based on these experiments. Flow around Reynolds-Shippen model, Reynolds number effect. Yeah, you know that we know Reynolds number is equal to VL by nu, and here the speed of model, if you compare the model and ship, the speed of the model is less, we see later it following the Froude condition, Froude hypothesis, and that is speed of model Vm is equal to speed of ship divided by square root of the scale, is not it, lambda, and model length is quite small compared to that of a real ship, maybe a 200 meter ship is modeled as maybe 4 meter. So, you can see that reduction in length. So, the Reynolds number VL by nu, here the nu remains more or less same because model test is done in fresh water and ship operates in sea water generally. So, what happens, it is water, the value of nu remains more or less same. So, only difference is coming at the numerator V and L compared to ship and model. So, the ship Reynolds number is much higher compared to that of the model Reynolds number, and you know that flow around the model, around the body, the boundary layer characteristic depends on the Reynolds number, and that means the flow around the model is going to be more in the laminar region, whereas the flow around the ship is going to be in the turbulent region. So, to perform a model test you need to have a condition of kinematical similarity to be satisfied, the fluid particle kinematics should be similar, which is not achievable between the ship and model. We will see later how we tackle this problem. So, the model experiments are carried out at relatively low Reynolds number, the reason I have said now, the flow around the model may be laminar. So, around the, because the Reynolds number is less, flow is going to be laminar around the model. For a ship which operates at high Reynolds number, ship will have a high Reynolds number, as I said before, the flow around is generally turbulent. So, there is a mismatch, here it is laminar and here it is turbulent. So, kinematical similarity is not achieved. So, prediction of ship resistance from model test involves assumption that model is full turbulent. That means, to achieve high kinematic similarity, you have to generate turbulence around the model also. So, every attempt should be made to ensure that a turbulent flow exists around the model. So, we have some techniques how to generate turbulence around the model to give more resemblance with the flow conditions around the ship. Then only the prediction of resistance from the model will become acceptable when it gets extrapolated to the prototype. So, you can see that the bow of the ship model, local Reynolds number is low, because bow is a small length, if you consider maybe 10% of the length, so it is very small. If the local Reynolds number is low even for the model and also even for ship also. So, the front region of the ship, that is a forward region of the ship, and also the model will have a laminar flow condition, and there is a negative pressure gradient because the velocity increases. So, the chances of laminar and partly laminar flow at the bow is very high. So, the bow part usually will have a laminar condition because the local Reynolds number is less and the flow will be laminar in the bow part of the vessel. So what you do in resistance test is to get some resemblance between the ship and model flow conditions, you try to stimulate turbulence using some technique. So turbulence is created around the model to somewhat match with the ship flow. It may not be matching exactly with that of the ship, but it is better to have some turbulence having no turbulence. So you just induce turbulence there. The technique to simulate turbulence can be divided into two. One is you create turbulence, the whole flow coming to the model is turbulated, or you create turbulence only in the boundary layer. There are two options. So you disturb the flow, create turbulence just before the flow reaches the model, or you aim only for the boundary layer of the model which get the turbulence. Both are acceptable. So that is what the artificial creation of high turbulence level in the area of the water in which the model, that is water itself is in turbulent, or artificial turbulent disturbance in the boundary layer. So these are the two options you have. So here we see what happens, we disturb the flow ahead, turbulence stimulation ahead of the model. So what are the options you have? So you have the carriage, in the carriage you can fix, extend an arm, you can fix something like this, that is a net, you put small net. When the flow passes the net, it induces turbulence. So the whole flow around the model will be under turbulence. So that is one of the technique here. So you have a net, which this will form part of carriage. So when it moves forward, the flow is coming from here to here. So when it passes through the net, it becomes turbulent and the turbulence is stimulated. Next is same, put an array of rods, small rods. Again when the flow passes through that, there will be a flow separation, turbulence created, or maybe a screen of water jet. You just put small water jet screen in front, so which also induces turbulence. So the whole model will be under the turbulence region. Another thing is now looking to the boundary layer, how you induce the turbulence in this, that is the second option. So what you do is you put a sandpaper strip over here, so it is rough. When the flow passes over this, there is a turbulence created. So this turbulence will extend in the boundary layer. So the boundary layer becomes turbulent. Next option is putting a tripwire. A tripwire is placed usually at 19th station, and when the flow passes the tripwire, flow separates and you get a turbulence in the boundary layer. And you know that this is the method what we are adopting here. So and usually it is put 19, that is 5% away from the forward perpendicular side, that is waterline intersection point. Why this region, why it is put at 5% is, we have already seen that the local Reynolds number is less. So in the ship and also model, even if you consider ship also, the local Reynolds number is less. So even for a ship, I think we have seen before one of the diagram, it is going to be laminar, isn't it? Just see that we had a picture which is obvious from that. Yeah, so you can see here, this is a ship, see the forward side and after that. See here it is almost very smooth flow, isn't it? It is a laminar flow in this region, the forward end. So and then it picks up and becomes turbulent towards the aft. So that is what, because it happens, why it is laminar in the forward region is, it is a local Reynolds number is less. Local Reynolds, so the flow becomes laminar. So in the, when you perform the model test also, you create a situation where the forward side will have a laminar flow and turbulence is created only after that. So that is why this tripwire is placed at the 19th station, that is 5% aft of the forward perpendicular. Another option for turbulence stimulation is in model is studs at the forward. You put some studs, just small, projecting slightly out, and again when it passes, same as sandpaper, so when it passes it creates turbulence. One more option which is rarely tried is the internal vibrators, that is outside the hull will be smooth outside, you have vibrator, it's a high frequency vibrators, you vibrate it, then due to vibration the flow get disturbed and turbulence is created, and usually this is not tried because it is dangerous, because high voltage is required for that, and generally it is not tried. Another factor in frictional resistance is roughness. So far we have considered generally a smooth surface, and the causes of roughness is structural roughness. This is coming to the actual ship case, not the model. Model is usually smooth, wax model or maybe fiberglass model, or smooth, so the surface is smooth. So the resistance predicted from such a smooth surfaced model does not match actually with the prototype, because prototype surface is not going to be as smooth as the model surface. So the prototype will be more rough due to various reasons. So some of the reasons here depends on the method of construction of the hull, whether you are going to have a welded ship, or whether you are going to have a molded like fiberglass, or whether you are going to have riveted joints. So all these methods, if the rivet is, the roughness is more, then the resistance, frictional resistance will be more, and depending on the type of weld, how many joints and everything, again there is a roughness factor which differs from ship to ship. Then openings, there are on the hull you may have different openings underwater, that is you have to get seawater for various purpose, ballasting, for seawater cooling of main engine, then for cleaning purpose, there for various operations. Though then you have openings on the surface which will naturally give more roughness to the hull surface, isn't it, which adds the resistance. Then the scoops, damage control, there are items, control valves and all that, which obviously have some hindrance to the smooth surface of the ship and which adds to the resistance, but compared to the ship size it is only a small quantity, but better not ignore it. Then waviness of plate between frames. So you see that ship construction is a stiffened plate, it is a plate which is stiffened inside. So between two stiffeners it is unsupported. So this plate during construction or during its operation can be subject to deformation. It may be a temperature reason or maybe a imperfection in the construction, various reasons contribute to that, and compared to the model there is a change, there is a dip and hump on the surface of the ship resulting in more roughness for the surface, and hence it increases the frictional resistance. So this is one of this, that is called come under structural roughness. So this is a reason of roughness for a prototype which is not envisaged in a model. Then a paint roughness, there are a lot of paints applied on the different layers of paint, primer, then anti-corrosive paints, anti-fouling paints, there are different layers of paints applied to the underwater portion of the vessel. The texture of the paint and application, manual efficiency, everything matters getting a smooth surface. So if there is a depending on these factors there will be a change in roughness which is not reflected in model. So that is what it says, good paints of partly reduce it, but paints of tough texture, depending on texture of the paint or badly applied, if the manual labor is not very skilled, then there is a problem. So all these things matters in increasing the roughness. So that is the one due to the paint roughness. Other causes are corrosion and erosion. Why the roughness increases compared to that of a model? Seawater or steel plate is very sensitive to seawater, which results in corrosion. Due to corrosion there will be a surface roughness increases, and so that is why proper cleaning and dry docking of ship is mandatory once in 2 years. That is, you have to take the ship to a dry space, then you chip the surface, repaint it and put it back to operation. This is mandatory for all ships, otherwise corrosion, if there for a longer period, it will eat away the plate, then the ship strength comes down and the ship may collapse. So it should not occur. from safety aspect also, and for the life of the ship it should be done. Then another is the marine growth. So it is under better surface of the ship, which ship is put to operation. It has been there for many months, and over the period you know that there will be a sea living beings getting started living on the better surface of the better surface of the body of the ship, and you see accumulation of seaweeds, barnacles and all that on that surface, and this obviously increases the roughness drastically, and thus the frictional resistance. So which should be avoided. There will be, when if this continue to be there will be lot of fuel consumption, cost increases. So in what all respect it is not a good thing. So you have to see that these weeds and everything are removed periodically and cleaned and put to operation. So that is what is this surface reduce resistance increases, periodic cleaning and use of anti-fouling paints reduce that. So if you put an anti-fouling paints, it will become it will reject, or it will reduce the chances of fouling. So the increase in resistance will vary with the type of roughness, is obvious. The types of roughness vary from ship to ship and also vary during the lifetime of the operation of the ship, isn't it? If it is a beginning new ship put to operation, initially there is no growth and everything is less, so it is roughness is less, but over the course of time the accumulation of biological growth increases, and roughness increases and resistance increases. So that is, as I said before, periodically should be cleaned and repainted. Then the model of a ship correlation elements given to determine model resistance accounts for ship roughness. So the model resistance, this roughness is not there. So what you do is, when you extrapolate the model resistance to ship resistance, you have to give an allowance for this roughness, which is called the model ship correlation allowance, to account for the change in roughness between the model and the ship. So that is the what you call here the ship correlation allowance. So by and large we have covered what is the frictional resistance. We have seen started with what are different components of resistance. We have seen the two major components are frictional resistance and wave making resistance, and we have seen what how the frictional resistance is represented, how it is estimated using, finally we have said the ITTC formula, that is 0.075 by log r n minus 2 the whole square. That is the formula which is used to find out the frictional resistance coefficient of a ship. And the reason also I have mentioned why this is depending on experimental data, as getting it numerically it is difficult, and getting it even from experimentally from a model test also is not possible, because there is no kinematical similarity between ship and model. Reynolds operates a different Reynolds number, and hence it is not possible to get the frictional resistance obtained from model just extrapolated to the prototype. So these are the aspects related to frictional resistance.